Hello and welcome back to this 10th edition or lesson of Introduction to Trigonometry. And in the previous lesson, we discussed extensively the tangent, but we're going to repeat what we learned from the tangent. And we're going to repeat, actually, we're also going to repeat the link that many students fail to remember, which is not something that you memorize again. This is the simple, we said, cosine function, y equal cosine of x. And remember when we spoke about, how we were inside a unit circle, or any circle that you can call a unit circle. I call it the first circle because that's the first rotation, the first 360 degrees. We took that rotating vector, the tip of the rotating vector, on the horizontal axis. We did the vertical. I showed you the vertical. On the horizontal, if you take those segment length and then you take them out and you try to animate them as a heavy rope, they give you this function, which is the cosine function. Now the cosine function, starts right here at 1 and then goes here, and 0 here. 0 is represented here, which is like any coordinate grid, 0. But, in the other coordinate grid, in the normal one where you have a function like y equal x plus 1, you have 0, 1, 2, 3, 4. Here you are putting, many students get confused, and I get asked this all the time. Pi over 2, 3 pi over 2, pi, 3 pi over 2, and the 2 pi. Now, you are putting pi instead of 1, 2, 3, 4. You can think about it as 1, 2, 3, 4 and you can incorporate your ones here because pi is basically 3.141592 and then it doesn't end, okay? So, or 22 divided by 7 in some books. So you can think about it this way, and this becomes, what is 3 something divided by 2? 3.1 divided by 2, almost a little bit more than 1.5. So basically your 1 is going to end up here. You can do that. You can think about it this way, and there will be a restriction on how to use it. And I mentioned something like that in the previous lesson, and I told you it's better to always, when you want to plot and you want to go, if x equal 1, you can do it. What is y, but it's better to, in this stage, since we're still doing the introduction, to start with if x equal pi divided by 6 or pi divided by 4 or pi divided by 3. You're, the ones that are inside a special triangle, so you can find the y easily. So basically we're putting this radian instead of a value, numerical value of 1, 2, 3, 4 for the x, because we took them out of that circle where they're representing distances related to that special angle that form the horizontal, in this situation, part or breakup of this vector in relation compared to the total vector or the total force. And it made that ratio. And when we took that ratio as a segment length and we are trying to represent it and sketch it here as we are animating it here. And this is what we get. And again, remember, we said this is very in line. This is your quadrant 1, because in quadrant 1, the cosine as a function is positive. So it's above the x-axis. And between pi over 2 and pi is your quadrant 2. And what happens to the cosine, in quadrant 2? The cosine is negative. That's why this one goes underneath the x-axis. It's very, very simple common sense. And then between pi and 3 pi over 2 is your quadrant 3. And in this situation, the cosine is also negative. And then it goes above in the light, goes from the dark to the light, right here at 3 pi over 2, all the way to 2 pi, which is your quadrant 4, where the cosine is positive. So again, this is very in line with your basic. Cosine is the adjacent side, and the cosine of an angle is the adjacent side divided by the total vector or the total force. We are just animating the segment length created on the horizontal part now here by themselves. We took them out of that circle, and that because we took them out of a circle that has angles of pi over 2 and pi over 3 and pi over 6 and 3 pi over 2, we can put here on the x-axis, we can use the radians, because this will help us. Those are the cosine and the sine are functions of frequency. Again, let's not forget that. This is equal y equal cosine of frequency times time. Okay, and the time is related because it repeats the same cycle. What's the cycle? The basic cycle. It goes from max, in this situation it's 1, and the max and the minimum are determined by what? By that, amplitude. Amplitude is referred to in math by this capital A. So this actually equal A cosine of x, and A in this situation is 1. So it goes from max to the midline. We call that the midline. In this situation, the midline is your y equals 0, or the x-axis, and then it goes down to the minimum, which is -1, because in this situation we put the range or y between -1 and +1. When we have something like y equal 2 cosine of x, then the range will become, y is between -2 and +2. And when we have something we said like half cosine of x, this will become, the range will become between -1/2 and +1/2. Okay? Now, and we did the same thing with the tangent, but we said with the tangent, because the graph is gonna stop and it doesn't have, it's undefined, right, where pi over 2 or 3 pi over 2 or minus pi over 2 is, that means, at pi over 2, minus pi over 2, or 3 pi over 2, where the cosine is gonna get to 0, there is no solution. It's undefined, because this is sine divided by cosine. Okay? And this is where your vertical asymptotes happen. So if I am starting in quadrant 1, that's what I mean. Look at this. This is your quadrant 1. So right here between 0 and pi over 2 is my quadrant 1. And if I'm starting in quadrant 1 and I'm going to go, what happens to the cosine very close to pi over 2? The cosine very close to pi over 2 is gonna get to 0, but it's not really gonna get to 0 until it gets to pi over 2. And if it gets to pi over 2, this the tangent equals sine divided by cosine, you're dividing something by 0, so it's undefined. We won't have a solution. That's why we have this vertical asymptote. And we said when this whole thing, the tangent, approaches infinity, the distance between this vertical line or vertical asymptote and the curve itself, the animation of this tangent, approaches 0. But it's never going to get to 0, and it's never going to touch infinity, because infinity is just a concept. And then we spoke about the spread. We said the spread helps us determine the vertical asymptote. So you have a vertical asymptote. The first one is at pi over 2. So you say pi over 2 plus n pi. Here, let's go to the board for this, because this is actually, you can see that I'm very passionate about this. I'm passionate about this because honestly, when I was in grade 11, I did have a very hard time understanding how and why we are moving these pi and pi over 2 to the x-axis, and why we are relating the quadrant to the x-axis, and how this whole vector that we split up is relating to this animation of a sinusoidal wave. And I had to figure it out by myself, unfortunately. Anyways, so we have our x-axis, y-axis, something very simple, and I have a 0, and I have a 2 pi, and I have a pi in the middle, and a pi over 2, and a 3 pi over 2, and I'm just going to take the minus pi over 2 here. I'm not going to go. And then we said because y equal tangent of x or theta, now I do have my vertical asymptote where the function is not gonna exist. We can't divide by 0, okay? And then we said that the vertical asymptote is determined by the location on the graph or on the coordinate grid where the function doesn't exist. So it's basically the first one is pi over 2 plus the spread. What's the spread? And I did something like that, minus pi over 2 plus pi over 2. So your spread, this is for the spread though, not for the domain, okay? This, because the domain, if you restrict it, it will be like this. It's not going to have the pi over 2 and the minus pi over 2. The domain will be minus pi over 2 plus pi over 2 if restricted. Just for, you know, between the minus pi over 2. It's not going to have an equal here, okay? The spread is pi. This is how, you know, it's spreading, but it's n pi. Because n can go into the negative, it's an integer, or in the positive, okay? And we determined in this situation, we can say the domain is x, such as this vertical bar, x is not equal to this vertical asymptote, pi over 2 plus n pi, okay? Now the thing is, I went ahead and I drew it like this. And a while back, actually that was like maybe 2 years ago, I had a student ask me, why isn't it like this? Like the cotangent, which we're gonna deal with, you know, and very soon. Why didn't you go like that? And simply because, again, quadrant, 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 location, location, location. What's between 0 and 1? It's your quadrant 1. So in quadrant 1, if I do it like this, okay, that will give me what? Will give me a graph in the negative section under the x-axis. But in quadrant 1, both sine and cosine are positive, so it has to be above. And this is representing which quadrant? Here. This is representing not quadrant 2. Quadrant 2 is between pi over 2 and pi. So when I repeat, this is my quadrant 2. And in quadrant 2, sine is positive, cosine is negative, so the graph should be negative. In quadrant 3, they're both negative, so the tangent is positive. That's why it goes like this. In quadrant 4, what happens in quadrant 4? Again, it's gonna come like this. So it's gonna be negative because the cosine is positive and the sine is negative. And again, because this is a repetition, this is the end, this is a quadrant 4 here. So you need to conceptualize it as, if we start between minus pi over 2 and pi over 2, the distance between minus pi over 2 and 0, this is representing a quadrant 4 of that cycle here. The cycle that, you know, if we're starting quadrants, 0 is where you start your quadrant 1. So you end up with a quadrant 4, of course, because you have 4 quadrants in a circle. And that's how you do your repetition. And with that, we also talked in the previous lesson, before we dig into the cotangent or other things, we spoke about, this is our domain. We talked about all that good stuff. We spoke about the stuff that some students are, that they're still having a problem with. How do you go ahead and figure out that, for example, 210 is 7 pi over 6, you know? And I said, you know, you can think about it as going to quadrant 3 from quadrant 1. So if you start at pi over 6 and you add, you know, a pi, because you're going 180, you know, so this is 6 pi divided by 6. So that's why I got to 7 pi divided by 6. And I gave another example, you know, the 225. Again, I'm going from quadrant 1 to quadrant 3. This is just repetition. You need to repeat and exercise and train your... And this is, since it's at the 25, I can try the pi over 4 and I add a pi to it. And this gives me what? pi over 4, which is 45 plus 5, plus 180, I'm sorry, makes 225. So that's it. This is the one. So this is 4 and 4, right? So that's 5 pi over 4. And that's how I know these things. Not because, you know, there's no IQ here, or this is very easy. So, but you just need to train your, and if you're going to quadrant 2 from quadrant 1, you just add a pi over 2 and 90 degrees. So for example, if you want to go to 135 degrees, so you start at 45 plus 90 equal 135. So 45 is pi over 4 plus pi over 2. This gives you what? 2 pi over 4. So this makes the whole thing 3 pi divided by 4. There you go. Okay? All right, let's not waste any time on this. And let's go to, we want to talk about the clock. I promised we're going to quickly talk about the clock because you get that in many standardized testing. Convert from degree to decimal and from decimal to degree. And that's, I agree. This is a little bit confusing because you need, but we're going to try to make it as simple as we can. Before we do that, you know, your conversion should be something easy now. If they tell you, let's say, convert, let's say 127 degrees to radian, you should know that, you know, you don't need to memorize anything. You just stack them up like this, and then you go 127 degrees, and you find the fourth element, and you don't even need a scientific calculator here. And let me see here, what do we get? Get 2.2165. So you get a radian of 2.2165. Okay, let's do one that is a little bit not confusing, but should convert 25 radians. Not 1 radian, not 2 radians, radians. Okay, 25 radians, 2 degrees. And you'll be like, remember, the half circle is what? Is 3 and something, 3.1 radian. The whole circle is 6.28 radians. This special radian that we explained how we, you know, mathematician, you know, came up with that to calculate segments and sectors. You can go and review, I believe it was lesson 3 or 4. Now, I do the same thing. Pi, 180 degrees, and I put my radian on top now. And I do my calculation in 1,432.39 degrees. And you shouldn't be surprised, because 6 radians needs 360 degrees. So 25 radians is gonna need 1,000. That's what when you go to the ABC and you see like 1,432, I had a student one time. Yes, that's why we need to calm down. We need to understand what we're doing. And if you were not able to conceptualize that a whole circle, 360 degrees, takes only 6 radians, that you're not gonna, you know, be confident when you choose A equal, they give you A 1,432. They give you B 143, and some student, they go, oh, that's more, you know, I'll choose this. Again, you need to be confident. In order to be confident, you need to know your basics, okay? Now, let's go and talk about the clock, the famous clock. And then in many SATs and ACTs, and in many, you know, pre-calculus college test, or, you know, scientific faculties test, they give you something like this. Convert, which one I have here? 28 degrees, 43 minutes, 25 seconds to decimal. Okay. And then, you know, you are taught to solve it this way, which is, you know, perfect and correct. You are taught to say 1 minute, which is referred to in math as like this, equal 1/60th of a degree, or 1 degree equals 60 minutes. Okay, and that's perfect. So you come here, and then you go, okay, So I have 1 minute, which is one of those, like this, divided by, I'm stacking them up. I always like to do this, the equivalent fraction. 1 divided by 60 degrees equals what? What do I have? What was the question? The question was 43 minutes. Okay, so I have 43 minutes. So I put 43 right here. And my fourth element should be here. So in order to get this one, I have to do 43 times 1 divided by 60. So I come back here and I say 28 degrees plus 43, this one, times 1 divided by 60. And then I go to say, you know, the same thing, because look at this. The 1 second, like this in math, 1 second equal 1/60 of a minute, right? 1/60th of a minute, which is 1/3600 of a degree. So basically, if I go back to this one, to the question they asked me, they have what? 25 seconds. So I'm doing it this way in order to tell you that I don't, you know, I'm going to show you how not to memorize any of that stuff. So 25 times 1 divided by 3600. And then you do just the calculation and you get 28.72, I believe, 28.72. Okay, and that's 28.70. Let me see here, 1 second. Yep, 28.72. Okay, but the question is that most students, you told us not to memorize. Why should we memorize, or how do we know? And that's a very smart question, and this is a question that actually relates to a lot of scientific field. Why should we realize, and why should we memorize, and why should we that 1 degree is 60 minutes, or 1 minute is what? 1/60th of a degree. And how is that possible? How is that clock and minute related to that angle or degree? You know, 1 degree in that big circle here, you're talking about this circle, we did the pi over 2, pi over 6. This 1 degree here is 60 minutes. How is that possible? And that's a very legit question. And in order to solve that, you know, one day I'm going to do a series about, this has to do with geography of the Earth, actually, and the rotation of the Earth and time, perspectively. Like the Earth turns around itself, and it turns around the sun. But I don't want to confuse you. This is a very lengthy subject that is also linked to they're called the geographical and the spherical coordinate, that are related to the nautical coordinate and the directions, longitude and latitude, and the time zone. So again, it has to do with what? With time zone. So the angle of the Earth geographically is related to what? To time. So that's your first link. So time of the angle of the Earth, the angle, and then this is an angle, and this is an Earth on a plane, not in 3D dimension, is related to time. So that's your first link. And like I said, I promise one day we're going to do a full series. Some of you, they study that in something, they take like the bearings, they call it. The US Army and the Scouts, they use the bearings for direction. This is somehow linked, but it's more linked to the geography of the Earth and the angles at which we perceive the longitude and the latitude and the time zones. Okay, so we'll do that one day. But to make it easier now, and just to, you know, put it in the back of your mind, why is 1 minute 1/60th of a degree, or 1 degree is 60 minutes? If you look at the clock, this is your normal clock, analog clock. It's divided into how many compartments? It's divided into 12. So this is wrong. This is not 12. You need one more. So now I have 3 and 3, 3, 3, and 3. It's divided into 12 compartments. Each compartment represents an hour. But it does have what? It does have 2 hands. One for the hour and one for the minutes. Exactly. So you have an hour hand and a minute hand. In some books, they call them the hands. They call them the needles. So basically, this clock has the same geometrical, and pay attention here. It has the same geometrical construction as a circle, as the circle we're talking about. But is that angle here representing 1 degree? No. Why? Because this is related to time again. Now, it's not like Earth. It doesn't have a 3D shape. But we're going to try to make it as simple as possible and that's how I started tackling this subject a long time ago. So basically, this geometrical shape is represented by a circle, but is not really finishing its mission. It's not finishing its mission if it starts here. Let's say it starts here, the hour, not here, like a 0, 360. When it goes all the way around, does it finish the mission? No, for 2 reasons. It doesn't finish the mission because the day is 24 hours. So it's 2 times that amount of rotation, or amount of time, if you want to call it. So this geometrical shape that is the clock is a circle. However, it needs to be, the hour hand needs to be swiped twice in 24 hours to complete the mission. So you need to swipe it twice. So you're looking at a shape that's supposedly in the back of your mind, when it goes from one end to the other, like, the unit circle, from 0 to 360 degrees, that's my rotation. When I tell you we go from one end of the diameter chord to the other end, that's what it means. From minus pi over 2 to plus pi over 2, this is my spread. This is how it's broken, this tangent, at pi over 2 and minus pi over 2. There is no function. I can conceptualize this. But here there's something hidden. Because when the rotation in front of your eyes finishes, the mission is not complete. This geography of the Earth is related to the Earth rotating around itself, around its axis and around the sun. And it has to do with the angles that it makes with the center of the Earth, and it has to do with longitude, latitude, and it has to do with the time zones are very related to that. So basically, the hour hand needs to be swiped twice in order to complete the mission. The mission is 24 hours. Everything is based on the day. The whole rotation of the Earth around itself, around its axis, and around the sun is based on 24 hours, not on 12. So you're seeing something, but the result and the mission is not, perceivable. You cannot see it. And that's the first hidden element. So in order to make it easier to my mind, you can approach it this way. We're not going to go into geography of the Earth now. We're just going to talk about, to complete the mission, this mission of 1 day, 24 hours, that's the first mission in really being, in really configuring what does the Earth do, rotating around itself and rotating around the sun. So to complete the mission, those 12 compartments of the hour hand, they need to be swiped twice. So they need to complete what? So if I have 12 compartments, or 12 hour hand, or 12 section on the clock, we're talking about the clock. They need what? 720 amount of times. I set 720 degrees, but in the clock, their amount of times, or ticks of times, I don't know. And they correspond, if I take one of those compartments, not 1 degree, one of those compartments, and I say one of those compartments, one section, one geometrical section inside that clock, is going to correspond to how many amount of rotation, or how many amount of time, or how many ticks of time, it's going to correspond to 60, because I divided by 12 and I'm going to divide by 12 here. So I get 60. And inside the clock, it's 60 minutes. Okay. So because 1 hour is 60 minutes. Now, why can I compare this one compartment in the clock with 60 minutes to 1 degree in the regular circle and say that 1 degree is also 60 minutes? Again, that has to do with the bigger picture, with the geography of the Earth. This is going to give you the more scientific and robust explanation, the longitude, the latitude, studying the Earth as a sphere, a 3D dimension, the angle, the time zones, the relation to the geographical and spherical coordinate. It's a little bit complicated, but all you can do, you need to remember, in order to keep it in the back of your mind without memorizing 1 degree is 60 minutes, you can say, you know, in the back of my mind, I can relate that clock that doesn't really represent the mission. Remember, the mission in the sine was going, this is the mission of the sine function. And then it repeats, okay? It's done between 0 and 2 pi, and then it repeats. The mission of the clock to make a day, 24 hours, is not complete in front of your eyes. It needs to be swiped twice. There is a hidden element. This hidden element has a lot of complication that we're not going to get into. We're just going to say that we're just using the simple equivalent fraction again. Those 12 hours, 12 hand hours, 12 compartments, 12 geographical section inside the clock circle, which is not really the circle representing the total mission, needs 720 ticks of time, amount of rotation. So one of them needs 60 ticks of time, or 60 minutes in this situation. And I can go ahead and I can compare that to the unit circle or to any regular circle. And it's, instead of one compartment in a clock or one a geographical section in a clock, I can say 1 degree in a regular circle is 60 minutes. Why? Like I said, I promise we're going to do this. It's going to take us actually into beautiful horizons. We're going to link a lot of things together, from time zones to geography to longitude and latitude, and a lot of, fun things. For me, they're fun, but I don't want to confuse you now. Yes, you can, because it needs to be swiped twice to make 720 ticks of time, or amount of time. That means, 12 of them, like we said here, needs 720. So one of them needs 60 divided by 12. 12 divided by 12 equals 1. 720 divided by 12 equals 60 minutes. And we can relate that to that angle in a regular circle. So basically, we went back to say 1 degree is 60 minutes, or 1 minute is 1/60th of a degree. Now, they can ask the question differently. And what I mean by differently is they can tell you convert, which one I have here? 57.56.5692 to degrees. We want to go to degrees now. Degrees, minute, and seconds. Okay, we follow the same rule. So basically, 57.56 is your decimal form. We're going to degrees and minute and seconds now. So we go 57 degrees, right? Plus this whole decimal part, this is where the fun starts. This is where we're going to apply what? We're going to apply 1 minute is 1/60th of a degree. So what do I have in the decimal part? I have 0.5692, right? So in order for me to get that, what do I do to get the fourth element? I do 0.5692 times 1 divided by 1 divided by 60. That means times 60. So here I can go ahead, and this is my fourth element, which is 0.5692 times 60 and that's minute, the whole thing. And I believe I did this one here for you. We get like this. So this is the first step. The first step, we get 57 degrees plus 34.152. It's still, it's in the minute form, but in the minute form with somewhat, with some decimal in it. This decimal now, we need to transform it back to seconds. So again, I use the A over B equals C over D. I stack them up this way. And like we said, now we're going to use 1 second, which is 1/60th of a minute, right? 1 second is 1/60th of a minute. And now what do I have here? I have 0.152. So in the first situation, I use the minute with the degree. 1 minute is 1/60th of a degree, because we just talked about that now extensively. And we said, you know, we need to have it in the back of our mind, because it's swiped twice inside that clock. It doesn't really complete the mission until you swipe it twice. 720 degrees instead of 360, or 720 minutes, or ticks of time, or amount of time. So we ended up saying that, you know, your 1 degree is 60 minutes, or 1 minute is 1/60th of a degree. And the other part is very simple. 1 second is 1/60th of a minute. So this is something that you know already. I'm just doing taking that part, the second part, out of the decimal to represent it as degree, minutes, seconds. And I'm doing A over B equals C over D, just something very simple. So this thing here now equals what? Equal again 0.152 times 1 divided by 1 divided by 60, which means times 60. So I end up with something like that again. 57 degrees. Now I take the 34 without any decimal, so I can call it minute. Remember, it was 34.52, so it was minutes with some seconds with it. The same way in the beginning we had that 57.56 as degrees with some minutes and, you know, because remember very carefully, 1 degree is 60 minutes. So that was degrees with minutes and seconds in it, in the fractions, in the decimal. In order to get rid of that, I just stack them up in 1 minute is 1/60th of a degree. Where did I get that? From that special, you know, understanding of, you know, in a clock, the shape of the clock doesn't really help the mission. We need to swipe it twice to get 720 amount or ticks of time. And then we will divide that by 12 compartments to get to 60 minutes, to make 1 degree or 1 section in a clock equal, you know, 60 minutes. And we can make it equivalent to the 1 degree in a big 360 degrees circle. And the link between them is something that we're going to study, because it's very broad. Has to do with science, geography, rotation of the Earth, and rotation of the Earth around itself, around the sun, longitude, latitude, you know, and time zones. So, but for now, all we need to know that 1 minute is 1/60th of a degree. And then the second part is very easy, because you already know that 1 second is 1/60th of a minute. So all I did now is just come back, separate. Now I have it separated, so I can write 34 minutes. Plus, what do I have? 0.152 times 60. The whole thing is seconds. What do I get? I get, I didn't do this one. Okay, I get something like 9.12. So, I don't want to take that 12, because that's fraction of a second. They want me to write it as degrees, minutes, and seconds. So all I can do is I can come back here and write 57 degrees plus 34 minutes plus approximately 9 seconds. Okay? So I don't care about this, because they don't want the, you know, the fraction of the second, the 10th of a second. Okay, they just said write it in degrees, minute, and seconds, and that's what you get in most of your tests. They don't want the fraction of the second. So the key here is to remember that yes, you can relate the clock to this 1 degree inside a 360 degrees regular circle, plane circle, on a 2D plane. However, in order to understand it very well, that's a very broad subject that we will deal with later in the future. But all you can think about is the mission. The mission of the clock is to finish 24 hours a day. That's what we live by, day and night, 24 hours. And that's the basis of the rotation of the Earth around itself and around the sun. Okay? In order for that to be done, you need more than 360 degrees or ticks of time or amount of time. You need 720. You divide it by the 12 compartments of the clock, you get 60 minutes. And you can relate that to a regular circle. Okay? That's enough of this. We still have time. The last thing I'm going to talk about, next time we're going to start with the inverse function and with the vertical and the horizontal shift. But now we need to do the cotangent and just, separate it from the tangent and see. It's very easy. Just going to do y equal cotangent of theta or cotangent of x. Again, a is 1 here and b is 1. Now, what is the period of this function? The period of this function is pi. This is the spread. But your domain is what? Is 0, pi. Because at 0 pi, what's the cotangent first of all? Cotangent equal cosine of x divided by sine of x, right? We all agree to that. And since the sine of x is in the denominator, there comes a time when the function is not going to be, has no solution, when the sine of x equals 0. And what that happens at 0 and pi, right? So at 0 and pi, I have those vertical asymptotes. So this is when vertical asymptotes are equal to what? To 0, that's the first one, plus, what's the spread? It's between 0 and pi, because between 0 and pi, I can draw the function, but after that, after pi, I have to stop, so I'm breaking, so that's the spread. So the spread is pi, so plus pi n. N is the integer. When I go to the negative, n becomes negative. And the period is not gonna equal, remember, f equal b equal 1 divided by p, 1 time, 1 mission divided by the period. So when we go to the period is gonna equal 1 or 2 pi in the case of the sine and cosine to finish the mission. And when the tangent is involved, it's just pi. And when the cotangent, it's the same thing. It's pi divided by b. And b in this situation is 1. So it's the period is 1. So your regular period is 1. And the domain, again, is x, but such as x is not equal to those vertical asymptotes. 0 plus pi n or pi n, okay? And the range is minus infinity plus infinity. Now, let's go ahead and sketch it. And it's very easy to sketch again. So if we go ahead and we take, let's say this. And now we have the vertical asymptote at 0 and at pi. So this is pi. This is the 2 pi, right? And I can go ahead here and make a minus pi in the negative. And I can come back here and draw my pi over 2 and draw my 3 pi over 2. Now, what happens at pi over 2? At pi over 2, y equal cotangent, which is cosine divided by sine, right? At pi over 2, what's the cosine? Cosine is 0, and the sine is 1. So it's 0. So this is your, And how do I know now that it goes like this? It's going to go like that. And not like this. We just talked about it. This is no. because that's for the tangent. The cotangent goes the other way around, spreads the other way around. Why? Again, in quadrant 1, it has to be positive because this is quadrant 1 between 0 and pi. In quadrant 1, it has to be positive because, and then here again it goes back like this. In quadrant 1, it's cosine divided by sine. They're both positive, so it's positive. In quadrant 2, it's underneath the x-axis. In quadrant 2, the cosine is negative and the sine is positive, so it's negative. In quadrant 3, you see it here, it's positive. They're both negative. Negative divided by negative, it's positive. In quadrant 4, the cosine is positive and the sine is negative, and that's why it goes underneath the x-axis. Something very, very, very simple. And if you want to talk about it differently, if you want to come here and say, let's say, what happens at the 0? What happens at the 0? We're not getting to 0 because at 0, the sign becomes undefined. There is no sign. You know, the sign becomes 0. And then with the whole thing, the cotangent becomes undefined. That's why we have a vertical asymptote. There is no solution here. So, and the cosine at approaching 0 becomes very, very, very large because its biggest value is 1. So we have a cotangent which has a very, very, very big value here and a very, 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 very tiny value that is approaching 0 but not really 0. That's why we are going, you know, in the direction of infinity, because we have a very large number with a very tiny infinitesimal number in the denominator. So that's why it has to be on this side, approaching plus infinity. And if you go to quadrant 2, it has to be approaching minus infinity because the cosine is going, you know, and it's becoming very, very, very large, but approaching minus 1. A negative value, its largest negative values. That's why it's going in this direction, approaching minus infinity. Okay, now we still have time. We're going to actually do the secant. Let's start with the secant. Y equal, and I had a few demands to do the secant and the cosecant. And again, they're not really difficult if we just follow what I've been, you know. How do I know first what is the secant if I forgot? Again, TSC, tangent, sine, cosine, cotangent, and cosecant, which linguistically it means next to last, and secant, which is last. Now you can go ahead and do it like this, and you can say that you can go clockwise, remember, and counterclockwise. It doesn't matter, it's the same. So if you go this way, it's tangent divided by sine, and tangent, you already know it's sine divided by cosine, times 1 divided by what? By sine. So sine and sine, we eliminate them. It's 1 over cosine of x. And then you can figure that out with the product identity, which has 1 in the middle. So 1 equal, 1 is right here in the middle, equal the two other ends, cosine times secant. So secant is the reciprocal of the cosine, not the sine. So equals 1 divided by cosine alpha or cosine x. So basically I have a function that has a cosine in the denominator, and that's not very, so f of x or y equal 1 divided by cosine of x. So the thing is here, you have 1 divided by the cosine of x. It's not tricky, but you know, this is common sense. So basically it's in the form of a fraction, right? But is it a proper or an improper fraction? Remember, this cosine is always between -1 and +1, right? So it could be right at 1 and -1 because of this, but it's, you know, it's always under 1, under -1, larger than -1, but you know, with the absolute value under -1. So basically, this is a proper fraction. This is, you know, you're dividing small, tiny cosine as a fraction. It's a ratio, remember? So it's as if you're dividing 1 by 0.25, which is, you know, how many 0.25? It's 4. The number is big. And or 1 by 0.5, which is which is the half. And again, it's 2. So between 1 and -1, there's no function. because all the sketching that you're going to do is going to be, you're going to, this one and this in the middle, there will be no function. Because at the end, you're going to, for the whole thing, for y equals secant x, you're going to get something above 1 and, under -1. So between -1 and +1, that's the first thing I want to put in my hand because it's common sense. There is no function. I cannot sketch anything there. Now the period has to follow the cosine because the cosine is in the denominator. My period is 2 pi. However, the period to finish one mission, period, here is 2 pi divided by b. I don't have the other element like in the tangent and the cotangent, where that's how I restricted it. The restrictions happens here between -1 and +1, because between -1 and +1 I cannot sketch anything. There is no solution. Because the cosine is in itself a proper fraction, it's a very small number, I'm always going to end up with values under -1 or above +1. Okay, so my restriction is not at a vertical asymptote. My restriction is between -1 and +1. So my period follows the cosine. It's 2 pi divided by b. Or in this situation, b is 1, so it's 2 pi. So I solved the period. Now, however, the spread is limited to pi y because the cosine is in the denominator. So what do I mean by the spread? This is what I mean by the spread. Look at this. The domain is going to be x, but such as x is not equal to what? To pi over 2, 3 pi over 2, minus pi over 2, which is what? Where the cosine becomes 0. When the cosine becomes 0, there is no solution. So there is no graph. So basically, I do have vertical asymptote. Oh, look at that. It's not complicated. It just has a restriction between -1 and +1 and vertical asymptote. So there is a location on that coordinate grid where there is no graph. Those are your vertical asymptote, plus pi n. Not 2 pi n, because at pi over 2, 90 degrees, there is no cosine is 0. No solution for the secant. If you move down 3 pi over 2, again you moved a pi. If you moved back to minus pi over 2, you moved a pi or minus pi. So plus pi n. This is your domain. Your range now is somehow not minus infinity plus infinity. Remember, there's nothing between -1 and +1. So my range is going to be minus infinity, including -1, union +1 all the way to plus infinity. And when we draw it, it's going to be very easy for you to, conceptualize. Look at that. It's not really something, the problem is we had two restrictions. One with a vertical asymptote because the cosine, there is something in the denominator still that is going to make the function undefined or no solution. And at the same time, what's in the denominator compared to the numerator, which is 1 and always 1, stable, is a small fraction. So that's why the solution are going to be always a proper fraction, larger than 1. So that's why between -1 and +1, there is no solution. That's why the range is this union, including the +1 and the -1. Now we said the vertical asymptote are at your famous pi over 2 and 3 pi over 2. And if this is the 2 pi, this becomes what? What's 3 pi over 2? 270. 270 plus 180 plus the pi. We said the pi is a spread. It's 450. And 450 is 5 pi over 2. So I do have also, this is the 3 pi over 2. And this is the pi over 2. And this is again the minus pi over 2, where the cosine is 0 and where there is no solution. And now I can go ahead and do, now if I want to be very precise, we said pi over 2 is almost 1.5. So if this is 1.5, 1 is somewhere here. So this is my 1 here, my +1, and this is my -1, okay? And I want to go ahead and draw that. So at +1, what makes that secant a 1? What makes the secant of 1? Cosine of pi over 2. It has to be 1 here, right? What did you say, James? Hold on one second. Let me check my text here. Yes, it has to be 1. 1 is included, and -1 is included. So it has to come this way. This is your vertical. It has to come this way. In between, and here at the pi, this is the pi, it has to be -1. And it's going to go like this. And again, it's going to repeat right here at the 2 pi. And it's going to go like this. Now, if we think about it as quadrant, what's in quadrant? This is your quadrant 1. In quadrant 1, it's a secant, right? So equal 1 over cosine x. So in quadrant 1, the cosine is positive. So it has to go positively. And when it's pi over 2, there is no solution. But as it approaches pi over 2, the cosine get very, very, very small, and this whole thing goes to infinity. So that makes sense. At 0, cosine of 0 is 1, and 1 divided by 1 is +1. That's why we have the 1 here. In quadrant 2, what happens in quadrant 2? In quadrant 2, your cosine is negative. So it's at pi exactly, it's -1. So this becomes 1 divided by -1, so it's -1. That's why we have to include that -1 here. But between pi over 2 and pi, the cosine at pi over 2 does not exist. After the pi over 2, the cosine becomes negative. That's why it's negative here. And the cosine in quadrant 3 is also what? The cosine in quadrant 3 is also negative. That's why it goes this way. Okay? And in quadrant 4, your cosine is positive. And at 2 pi, the cosine is 1. So 1 divided by +1 is +1. And see, this is the restriction here now. This area here, this is the range restriction. So again, we will repeat it in the next lesson, and we will do the cosecant, which is very similar. However, here, the trick is, it's not really a trick, it's just you need to fathom and understand that the cosine in itself and the sine in themselves, they're proper fraction. They're under 1 as absolute values. So when you put, not in the case of a tangent, in the case of the tangent, you have both of them, the sine in the numerator, the cosine in the denominator. But in the case of the cosecant and the secant, there is a stable 1, a value up there, and you have a smaller value that gets smaller and smaller. So the whole function, the ratio, this ratio is always either above 1 or under -1. So that's why we have this restriction also in your range. So the range is a union between -infinity, including -1, and then +1 all the way to +infinity. It includes the -1 and the +1 because at pi, cosine is -1, and the whole thing becomes -1. And at 0, cosine is 1, and the whole thing, the secant, this reciprocal identity becomes 1. So 1 and -1 are included, but the distance between them, the length between them, is not included. Okay? And your vertical asymptote we've been working on these. They're very easy to decipher. You just look at what's in the denominator. If you have a cosine, so it's the pi over 2, minus pi over 2, 3 pi over 2, 5 pi over 2. And this is where the function is undefined and there is no solution. Okay? So with that, I'm going to leave you with that. Before we dig into inverse functions and vertical and horizontal shift in the next lesson, we will do the cosecant, just to recap, which is very similar to the secant. And then we will start the inverse functions. Okay? Thank you, guys.